4 astronauts flew around the moon in 2026. They went farther from Earth than any human in over 50 years. They saw the far side. They came home safely. And they never landed. We'll uncover the heat shield flaw nobody announced, the fueling problem that grounded the mission, the political war over funding, and a biological discovery that changes everything about who goes next. If you want the full story, stay with us. And if you enjoy what we do, a like and subscribe means the world. Prepare yourselves. We begin. The announcement came with flags, press conferences, and the kind of excitement that makes people believe history is about to happen. NASA said humans were going back to the moon. The whole world heard "going back" and filled in the rest themselves. Landing, footprints. A moment like July 1969, replayed for a new generation. Artemis 2 delivered none of that. What it delivered was something genuinely remarkable and genuinely misunderstood. 4 astronauts climbed into the Orion capsule, rode the most powerful rocket ever built off the surface of Earth, looped around the moon at roughly 5,800 miles above its surface, and came home. No landing, no descent, no boots on grey dust. The mission was always designed this way. NASA's documentation made that clear. Artemis 2 was a crude flight test. A shakedown run. The goal was to prove that humans could survive the journey inside Orion, that the life support worked, that the navigation held, and that the crew could handle the psychological and physical reality of deep space before anyone tried something as dangerous as touching down. But most people never read the documentation. They read the headlines. And the headlines said, "Moon Mission." So when the capsule splashed down in the Pacific and the astronauts climbed out without a single moon rock in hand, the confusion was immediate. Why did they go all that way and stop short? The answer has layers. Some of those layers are engineering, some are political, some are biological, and a few of them are things NASA was careful not to say loudly in press releases. Here is the first layer. Artemis 2 was built on the assumption that other things would be ready. Specifically, a landing vehicle. NASA chose SpaceX's Starship to carry astronauts from lunar orbit down to the surface. That vehicle had its own development timeline, its own test program, its own failures and recoveries. Starship needed to demonstrate orbital refueling before any human would climb inside it above the moon. That demonstration had not happened at the time Artemis 2 flew, so there was nothing to land with, even if the crew had wanted to try. That single dependency, one vehicle waiting on another program's readiness, is part of why the most powerful rocket ever assembled carried 4 humans around the moon and brought them straight home. But there is a second layer that received far less attention. During the uncrewed Artemis 1 flight, in late 2202, engineers monitoring the Orion capsule found something unexpected. The heat shield, the curved ablative layer designed to protect the crew during re-entry at speeds close to 25,000 miles per hour, had shed material in a pattern that models had not predicted. Chunks came off in ways that suggested the thermal loads were behaving differently than simulations showed. Nobody announced this as a crisis. The language was careful and measured. Anomaly under review. Engineers went back to the data. They ran new models. They found that the re-entry corridor, that narrow window of angle and speed the capsule has to hit perfectly, or risk burning up, required a more conservative approach than originally planned. Fixing that understanding took time, and time, in a program already stretched across budget cycles and congressional hearings, costs more than most people realize. So Artemis 2 flew. 4 humans rode farther from Earth than any crew since Apollo 17. They saw the far side of the moon in total radio silence. They came home, and somewhere in the data they brought back was a signal that would quietly reshape everything planned for Artemis 3. That signal pointed to a problem nobody expected to find this late in the program. In 2017, NASA received a directive: return Americans to the moon. Do it faster than anyone thought realistic. Make it sustainable this time, a permanent presence rather than a series of flags and footprints. The program was named Artemis, after the twin sister of Apollo in Greek mythology, and the name carried weight. This was meant to be the completion of something Apollo started and never finished. The original schedule was aggressive to the point of being almost confrontational. 2024 was the target for a crewed lunar landing. That deadline came from political pressure as much as engineering reality. The previous administration wanted a moon landing before the end of a presidential term. NASA, an agency that runs on 4-year budget cycles tied to administrations that change every 4 or 8 years, built a plan around that pressure. To hit 2024, everything had to go right simultaneously. The Space Launch System rocket had to pass its tests. The Orion capsule had to prove it could sustain a crew. The human landing system had to be developed, tested, and certified. The lunar spacesuits had to be redesigned from scratch, because the suits used during Apollo were long gone, and the ones used on the International Space Station were built for microgravity, not for walking on a surface with 1/6 the gravity of Earth. Each of those programs ran on its own timeline. Each had its own contractors, its own subcontractors, its own supply chains reaching back across dozens of states and hundreds of congressional districts. That geographic spread was intentional. Spreading jobs across many states means many senators and representatives have a reason to keep funding flowing. It also means that when one part of the supply chain slows down, the whole machine slows down. The first major slip came with the Space Launch System itself. Development stretched years past original projections. The core stage, a massive cylinder standing over 200 feet tall, ran into manufacturing problems and cost overruns that pushed the first launch from 2017 all the way to 2002. By the time Artemis I finally lifted off without a crew, the 2024 landing target was already mathematically impossible. The target shifted to 2005, then 2006. By the time Artemis II flew, the landing had drifted to a date that changed depending on who you asked and which component they were responsible for. And here is the part that gets uncomfortable. Some of those delays were not purely technical. Congress controls NASA's budget, and Congress did not always fund Artemis at the levels the agency requested. In several consecutive budget cycles, the human landing system received less money than NASA said it needed to stay on schedule. Less money meant slower development. Slower development meant a later landing. The original Artemis plan also assumed something that turned out to be far more complex than expected: that a private company could develop an entirely new lunar lander on a fixed-price contract, on a timeline dictated by a government schedule, using technology that had never been proven in deep space. SpaceX had done extraordinary things in low Earth orbit. Deep space is different. The physics are different. The consequences of failure are permanent. Artemis II was, in part, the result of every one of those slips stacking on top of each other. The mission that flew was the mission that was actually ready to fly. Everything else was still catching up. What was catching up, exactly? The next chapter makes that specific. Standing on the launch pad at Kennedy Space Center, the Space Launch System looks like a cathedral built for a religion humanity hasn't invented yet. It rises over 320 feet into the Florida sky. Its core stage burns liquid hydrogen and liquid oxygen through 4 engines originally developed for the space shuttle. Attached to either side are 2 solid rocket boosters, each one taller than the Statue of Liberty. When they all ignite together, the system produces over 8 million pounds of thrust. For context, imagine the force of a small nuclear detonation, sustained for 8 minutes. That is what it takes to push an Orion capsule and its service module out of Earth's gravity well on a trajectory toward the Moon. The Space Launch System is, by measurable thrust output, the most powerful rocket ever successfully launched. It surpassed even the Saturn V, the legendary machine that carried Apollo crews to the Moon, in certain performance metrics. Engineers and space historians argued about the comparison for years before the first launch settled it with actual data. So with that much power, why couldn't Artemis II land? Because power solves exactly one problem: getting off the ground. Everything that happens after the first 8 minutes requires entirely different systems, vehicles, and capabilities that the Space Launch System was never designed to provide. The rocket's job ends the moment Orion separates and begins its coast toward the Moon. From that point forward, the lander has to carry the crew down to the surface, keep them alive while they work, lift them back into lunar orbit, dock with Orion, and then Orion has to carry everyone home across 240,000 miles of space. Each one of those steps requires its own vehicle, its own fuel, its own tested hardware. The Space Launch System cannot carry a lander. The rocket has a version called Block 1B that was designed to carry both the Orion capsule and a co-manifested payload, essentially a lander or supplies, on the same flight. But that version required additional development and wasn't ready for the Artemis II flight. The lander was always going to be a separate piece of hardware launched separately and waiting in lunar orbit. That architecture was a deliberate choice, and a controversial one. During Apollo, the lander rode on the same rocket as the crew. Everything launched together. Artemis separated those functions, which introduced a new dependency. The crew could only land if the lander had already launched, reached lunar orbit, refueled if necessary, and was ready and waiting. There was another complication buried inside the Space Launch System's design. The rocket is enormously expensive to operate. Each launch costs somewhere between $2 and $4 billion when you account for the full program costs. For comparison, the entire Apollo program, adjusted for inflation, cost roughly $150 billion across 13 years and 17 launches. The Space Launch System's per launch cost means NASA cannot fly it frequently and cannot afford mistakes. It means each flight has to carry as much mission as possible. It means delays are catastrophic to the budget. It means the pressure on every subsystem to perform perfectly on the first attempt is unlike anything in modern spaceflight. The rocket worked. Both Artemis I and Artemis II launched on schedule once they reached their final launch windows. The Space Launch System did exactly what it was built to do. The problem was everything waiting on the other side of the journey. And one of the most stubborn problems was something the engineers had discovered quietly, inside a piece of hardware most viewers never hear about. Re-entry is the moment every deep space mission either survives or doesn't. When Orion comes screaming back into Earth's atmosphere after a lunar journey, it arrives traveling at roughly 25,000 miles per hour. At that speed, the air in front of the capsule compresses so violently that it heats to temperatures exceeding 5,000 degrees Fahrenheit. The surface of the heat shield absorbs that energy by burning away in a controlled way, a process called ablation. The shield sacrifices itself so the crew doesn't. This technology worked on Apollo. Engineers spent decades refining it. By the time Orion was being built, the heat shield material, a compound called avcoat, was considered well understood and well tested. Then, Artemis I happened. When engineers recovered the Orion capsule after the uncrewed Artemis I mission in 2022, they expected to find heat shield wear consistent with their computer models. Instead, they found something that took months to fully analyze. Chunks of the ablative material had come off in a pattern that no simulation had predicted. The thermal protection layer had cracked and shed in discrete pieces rather than eroding smoothly. Some of those pieces were larger than engineers considered acceptable. The capsule survived. The temperatures never breached the crew compartment. On a crewed flight, the astronauts would have landed safely, but would have survived and performed within predicted parameters are two very different standards in human spaceflight, and NASA operates on the second one. The investigation lasted over a year. Teams at the Johnson Space Center, Langley Research Center, and the manufacturing facilities that built the heat shield ran tests, built new samples, exposed them to arc-jet facilities that simulate re-entry heating, and compared results against the Artemis I data. What they found was that the avcoat material behaved differently under the specific combination of heat, pressure, and duration that a lunar return trajectory produces, compared to the shorter, lower energy re-entries from low Earth orbit that most of their test data came from. The fix involved two things. First, a material adjustment in how the avcoat blocks were manufactured and bonded to the underlying structure. Second, and more significantly, a change to the re-entry trajectory itself. Orion now approaches Earth on a slightly different angle and uses a skip re-entry technique, essentially bouncing once off the upper atmosphere before coming in for the final descent. This spreads the heating load over a longer time at lower peak temperatures. That trajectory change sounds minor. It required recertifying the guidance software, revalidating the parachute deployment sequence, and reconfirming that the service module separation timing still worked correctly under the new flight profile. Every one of those recertifications took time. And because Artemis 2 was the first crewed test of the heat shield, flying it before those certifications were complete was not an option. So the crew trained and waited. And the heat shield was tested again and again and again until every number matched what engineers needed to see. When Artemis 2 finally flew, the heat shield performed. The skip re-entry worked. The capsule came down in the Pacific within sight of the recovery ships. But the year-plus delay caused by the heat shield investigation had cascading effects across the entire Artemis schedule, pushing back decisions on the landing mission that were waiting for Artemis 2 data before they could move forward. And Orion's heat shield was only one of the hardware surprises the program encountered. The next one was quieter, stranger, and came from a direction nobody had prioritized. People ask this question with genuine confusion, and the confusion is understandable. 60 years ago, engineers with slide rules and computers less powerful than a modern wristwatch landed 2 men on the moon 6 times. Today, with artificial intelligence, advanced materials, and decades of spaceflight experience, returning to the moon has taken longer and cost more than the original Apollo program. How is that possible? The answer reveals something uncomfortable about how technological progress actually works. Apollo succeeded through a combination of factors that no longer exist. First, money. At its peak in 1966, NASA consumed over 4% of the entire federal budget. The agency had more resources, relative to the economy, than at any point before or since. That level of funding allowed engineers to solve problems by building multiple versions of everything and testing them until one worked. Redundancy was the strategy. If a design failed, you built another one. Second, Apollo operated under a single, unified deadline that every person in the program understood. The goal was explicit, political, and tied to a Cold War competition that put national survival on the line, at least psychologically. That kind of pressure compresses timelines in ways that peacetime programs rarely replicate. Third, and this is the part people miss, Apollo accepted risks that modern human spaceflight programs are not allowed to accept. 3 astronauts died in the Apollo 1 fire in 1967. The program continued. During Apollo 13, an oxygen tank exploded and 3 astronauts nearly died in space. The program continued. The tolerance for loss was different. The public expected some level of casualties as the cost of frontier exploration. Today's NASA operates under a fundamentally different safety standard. After the Space Shuttle Challenger disaster in 1986 and the Columbia disaster in 2003, the agency restructured its safety culture. The acceptable probability of crew loss on a human mission is now measured in fractions of a percent. Every system must be analyzed, tested, and certified to a standard that Apollo never attempted. That standard is correct. It saves lives. It also multiplies the time and cost required to field any new system. There is also a supply chain problem that surprises people. When NASA decided to return to the moon, it found that many of the materials, components, and manufacturing techniques used during Apollo no longer existed. The companies that built them had moved on. The workers who knew the processes had retired or died. Some materials were no longer manufactured anywhere in the world. Engineers had to rediscover solutions, sometimes reverse engineering salvaged Apollo hardware just to understand what had originally been done. The Avcoat heat shield material required reconstructing a manufacturing process that had essentially been abandoned for decades. Beyond materials, the complexity of modern missions exceeds Apollo in ways that are easy to underestimate. Artemis is designed not just to land, but to establish a sustained presence. That requires life support systems capable of functioning for weeks, not days. It requires spacesuits that can handle the abrasive lunar South Pole terrain and the extreme temperature swings between sunlight and permanent shadow. Apollo suits were extraordinary achievements. They lasted hours. The new environment at the lunar South Pole demands suits that last for much longer operational periods, under conditions Apollo never encountered. Every one of these factors compounds. Each solved problem reveals 2 new ones. Each new certification requirement adds months to the schedule. Apollo went to the moon because the nation poured everything it had into the attempt. Artemis is going back under entirely different constraints, with entirely different expectations for what success means. And there is one specific constraint that shaped Artemis 2 more than any other. The people inside the capsule are not just passengers, they are data. Reed Wiseman, Victor Glover, Christina Koch, Jeremy Hansen. 4 people, 1 from Canada, 3 from the United States, a mix of military test pilots, scientists, and mission specialists. Wiseman served as commander, Glover as pilot, Koch and Hansen as mission specialists. Together, they formed the first crew assigned to fly beyond low Earth orbit since the final Apollo mission in December 1972. For over 50 years, every human being who left Earth stayed relatively close. The International Space Station orbits at roughly 250 miles above the surface. That sounds far. Against the scale of the Moon, it is nothing. The Moon sits 240,000 miles away. Artemis 2 crossed that entire distance. The journey to lunar distance and back took roughly 10 days. Inside the Orion capsule, the crew lived in a space about the size of a large SUV. 4 adults for 10 days, with equipment, food, hygiene systems, scientific instruments, and the psychological weight of being farther from any help than any human in a lifetime. People imagine astronauts as purely technical beings, calm and analytical in all situations. The reality is more physical. During the outbound journey, as Earth shrank in the windows, the crew reported a sensation that no simulation fully prepares you for. Earth stops looking like the ground you came from and starts looking like a planet. A sphere, something you could cover with your thumb. That cognitive shift, seeing your entire world as a small object floating in black space, produces what astronauts call the overview effect. It has been described as a sudden, visceral understanding of how fragile and isolated the Earth actually is. For Artemis 2, that experience was amplified by distance. Apollo crews felt it at 240,000 miles. Artemis 2 flew a trajectory that, at its farthest point, pushed the capsule farther from Earth than Apollo missions typically reached, briefly extending the record for the most distant humans in history. Inside the capsule, the crew ran continuous experiments. They monitored their own bodies. They took blood samples, logged sleep quality, measured how their sense of direction and balance shifted without a consistent gravity reference. They ate prepackaged meals calibrated for nutritional needs during high-stress operations. They slept in shifts to ensure someone was always alert. The Orion capsule, unlike the Apollo Command Module, was designed with crew comfort as a real engineering consideration rather than an afterthought. Improved lighting, better air circulation, a more ergonomic layout for sleeping and working, still cramped by any civilian standard, still an environment that required constant physical and mental discipline. The lunar flyby itself lasted only hours. As Orion swept around the far side, radio contact with Earth cut off completely. For approximately 25 minutes, the crew was in total communication blackout, alone with the Moon filling their windows, unable to reach anyone. That silence was not a malfunction. It was physics. The Moon blocked every signal. The crew knew it was coming, trained for it, and still found it unlike anything they had experienced before. What they saw in those 25 minutes was something no human had seen in over 50 years. And what they brought back in their bodies told a story that will directly determine who gets to land next. Between Earth and the Moon, there are 2 invisible walls that every outbound crew must pass through. They are called the Van Allen radiation belts, named after the physicist James Van Allen, who discovered them in 1958. They are regions of space where Earth's magnetic field traps high-energy particles, mostly protons and electrons, streaming in from the solar wind and from cosmic sources far beyond our solar system. Inside the belts, the radiation density is intense enough that unprotected humans would absorb dangerous doses in hours. The belts extend from roughly 600 miles above Earth out to beyond 25,000 miles. Apollo crews passed through them quickly and accepted the exposure as part of the mission. The total dose received by Apollo astronauts during their transits was documented and studied afterward. Compared to modern occupational limits for radiation workers on Earth, the Apollo figures were significant but manageable for short-duration missions. Artemis 2 took the same basic path through the same belts, But the context had changed. Researchers studying the long-term health records of Apollo astronauts found something troubling. A 2016 study analyzing cardiovascular deaths among Apollo crew members found rates significantly higher than astronauts who had only flown in low Earth orbit and far higher than non-flying NASA personnel. The researchers concluded that deep space radiation exposure might be damaging the lining of blood vessels in ways that increased long-term cardiac risk. That finding reshaped how NASA thought about the Artemis II crew's exposure window. The capsule provided some shielding, but Orion is not a fortress against radiation. The hull attenuates lower energy particles, but does little against the high-energy galactic cosmic rays that penetrate almost any reasonable thickness of material. The physics makes complete shielding essentially impossible with current technology. To minimize exposure, Artemis II was timed to avoid periods of heightened solar activity. The trajectory was optimized to transit the most intense portions of the Van Allen belts as rapidly as possible. The crew wore dosimetry devices continuously, measuring accumulated dose in real time. Small sensors were placed throughout the cabin to map the radiation environment spatially. The data collected was arguably as valuable as anything else the mission produced. Engineers needed to understand exactly how much radiation a crew accumulates on a lunar trajectory under varying solar conditions. That data feeds directly into the planning for Artemis III, where astronauts will spend more time in deep space, including time on the lunar surface, where there is no magnetic field and no atmosphere to deflect incoming particles. At the lunar South Pole, the target landing site for Artemis III, the terrain provides some shielding. Astronauts working inside permanently shadowed crater regions would have the crater walls blocking some cosmic ray angles, but working on the open surface means full exposure to everything the cosmos sends. The Artemis II crew's dosimetry data gave scientists the most precise measurement of deep space radiation exposure in decades. It also raised questions that researchers are still working through. One of those questions involves a biological effect that the crew reported, and that instruments confirmed that nobody had expected to measure on a 10-day flyby mission. That finding quietly moved to the top of the planning priorities for Artemis III, and it connects to a problem in human space biology that makes landing on the moon harder than any rocket science. Space has a temperature problem. 2 temperature problems, actually, and they happen at the same time. In direct sunlight, the surface of the moon reaches over 250 degrees Fahrenheit. In shadow, it drops to negative 280 degrees Fahrenheit. Those two extremes exist within feet of each other because the moon has no atmosphere to spread heat around. On Earth, air moves heat from warm places to cold ones. The moon offers no such buffer. For a spacecraft in lunar orbit, the situation is equally severe. One side of the vehicle facing the raw thermal radiation of the solar disk bakes. The opposite side, radiating heat into the cold vacuum of deep space, freezes. The Orion capsule and its service module cycle through these extremes repeatedly during any lunar mission because the spacecraft rotates slowly to distribute the thermal load. That slow rotation is called the passive thermal control mode. Crews sometimes call it the rotisserie maneuver. The Apollo astronauts used it. Orion uses it too. The idea is to prevent any single part of the structure from overheating or becoming dangerously cold by spreading the exposure evenly over the entire vehicle surface. During Artemis I, engineers monitoring the thermal control system noticed performance variations in certain heat exchangers inside the service module. The service module, built by the European Space Agency, manages the flow of heat between internal systems and external radiators. When heat exchangers behave outside their expected performance band, the entire thermal balance of the vehicle shifts. The deviations seen on Artemis I were within the vehicle's operational tolerances. The capsule and its systems remained safe, but the margins were narrower than models predicted. And narrower margins in thermal control translate directly into shorter operational windows and reduced flexibility during lunar surface operations. For Artemis III, the thermal situation becomes more complex. Astronauts working on the lunar South Pole surface will move between areas of intense direct illumination and deep shadow with extreme temperature differentials. Their suits must manage that transition without failing. The Orion capsule waiting in orbit must maintain its systems through extended periods with limited crew activity, relying entirely on automated thermal management. The thermal control findings from Artemis 1 and the refined data from Artemis 2 pushed engineers to revise the thermal models used for Artemis 3 planning. Specifically, the maximum continuous stay time on the lunar surface was adjusted based on how long the suits and the lander could maintain safe temperatures for the crew. This adjustment affected mission planning in a way that didn't make headlines but mattered enormously. The original surface stay duration for Artemis 3 was longer. The revised thermal models shortened it. And a shorter surface stay means less time to do science, collect samples and scout locations for future equipment. Every hour matters when you are landing humans on the moon for the first time in 50 years. The thermal data also revealed something about the lunar South Pole specifically that changed how mission planners thought about the approach trajectory. The permanently shadowed crater regions, the very areas richest in water ice, are also thermally hostile in ways that models hadn't fully captured until Artemis I flew real instruments through the environment. The ice was there. Getting to it safely required more careful planning than originally anticipated, and the ice is the reason the South Pole was chosen in the first place. That story goes deeper than most coverage suggests. Somewhere between the Earth and the Moon, in a strange oval orbit that swings close to the lunar surface on one end and reaches nearly 50,000 miles out on the other, a space station is being built. It is called Gateway. NASA describes it as a critical waypoint for sustainable lunar exploration, a place where crews can rest, resupply, and prepare before descending to the surface. It will be smaller than the International Space Station, more like a large habitat module than a full station, but permanently positioned to serve lunar missions for decades. The concept is compelling. A station in lunar orbit means crews don't need to carry all their supplies from Earth on every mission. Robots can maintain it between crewed visits. Equipment can be staged there. Scientific instruments can operate continuously. Over time, it becomes an anchor for a permanent human presence near the moon. The debate among engineers and mission planners is whether Gateway helps Artemis 3 land sooner or later. On the complications side, Gateway adds a rendezvous step that wasn't part of Apollo. After launch, the crew would travel to Gateway, spend time aboard, transfer to a lunar lander, descend to the surface, ascend back to Gateway, and then travel home. Each additional rendezvous is an additional opportunity for something to go wrong. Each extra vehicle that must be present and operational before the crew can proceed is another dependency on the critical path. Apollo went directly to the moon. 2 vehicles, 1 orbit around the moon, 1 descent. Artemis with Gateway involves more steps, more vehicles, and a longer mission duration. On the benefit side, Gateway allows mission architectures that would be impossible from a single direct flight. Longer surface stays become feasible when the crew doesn't need to carry all their return consumables down to the surface and back up again. The lander can be reusable, refueled at Gateway between missions, rather than disposable like the Apollo lunar module. Gateway also enables access to more landing sites. The unusual orbit Gateway uses, called a near-rectilinear halo orbit, provides access to nearly the entire lunar surface, including the South Pole, with relatively modest fuel expenditures. A traditional low lunar orbit would make South Pole access more expensive in fuel terms. For Artemis 2 specifically, Gateway was not yet in place. The first Gateway modules were still in manufacturing during the Artemis 2 flight. This meant Artemis 2 flew a direct free return trajectory rather than a Gateway integrated profile. But the schedule for when Gateway would be ready influenced decisions about when Artemis 3 could fly. If Artemis 3 was going to use Gateway, it needed to wait for Gateway. If it bypassed Gateway and flew direct, it needed a different lander architecture. These questions were actively being debated inside NASA while Artemis 2 was still in flight. And the answer depended partly on something that was happening at a private company facility in Texas and Florida simultaneously. Something that had failed dramatically, then succeeded, and then faced a problem that no aerospace program had ever solved before in operational conditions. If you could stand on the rim of Shackleton Crater at the moon's south pole and look around, you would see something that exists nowhere else in our solar system. that humans have ever visited. On one side, blazing sunlight falls continuously on elevated ridgelines that have been illuminated almost without interruption for billions of years. Scientists call these peaks of eternal light. On the other side, stretching down into a crater over 12 miles wide and nearly 3 miles deep, is permanent darkness. The solar disk never climbs high enough above the horizon at the South Pole to send a single photon of light into that crater's floor. The temperature inside that darkness sits at roughly negative 400 degrees Fahrenheit, colder than the surface of Pluto. Cold enough that volatile chemicals that would evaporate anywhere else in the solar system remain frozen solid, trapped for potentially billions of years. That is why Artemis is going there. The specific landing zone targeted for Artemis 3 sits on a ridge near Shackleton, close enough to access the shadowed interior, but high enough to receive nearly continuous sunlight for solar power generation. The terrain on that ridge is rugged, heavily cratered, and slopes at angles that make landing a large vehicle genuinely challenging. Landing on the moon is harder than it sounds, even in benign terrain. The moon has no atmosphere, so no parachute works. No aerodynamic braking helps. Every meter of descent must be controlled by rocket engines, guided by sensors, with a lander computer making hundreds of decisions per second. Mistakes are permanent. At the South Pole, the challenge multiplies. The low solar angle creates extreme contrasts of light and shadow that confuse optical navigation systems. Cameras and LiDAR sensors designed to read terrain features struggle when half the scene is brilliant and the adjacent area is impenetrable black. The ridgeline target is small compared to the flat plains Apollo landed on, and the terrain has never been mapped at the resolution needed for precision landing, using only orbital observations. NASA's Commercial Lunar Payload Services program was designed to address exactly this problem. Robotic landers were supposed to arrive at the South Pole before humans, carrying instruments to map the terrain in detail, measure the radiation environment close to the surface, and characterize the soil properties. Some of those landers arrived and operated. Some failed. The dataset they produced was useful but incomplete. The precision landing technology being developed for the human landing system incorporates hazard detection cameras that scan the surface in real time during descent and autonomously steer the vehicle away from dangerous slopes and boulders. This system was tested during Starship development, but had not been validated in the actual lunar South Pole environment. Before the planned Artemis 3 landing, the crater rim site itself holds the prize that justifies every technical risk. Below the rim, in that permanent deep shadow, water ice exists in quantities that researchers now believe may be enormous. The ice represents fuel, oxygen, and water for future missions. It makes the South Pole the most strategically valuable piece of real estate humans have ever attempted to reach. Getting there required solving problems that no previous lunar mission ever faced. And the most stubborn of those problems had nothing to do with rockets or navigation. It was chemistry and physics, and a challenge of moving material from one vehicle to another in the vacuum of space, while both vehicles traveled at nearly the same speed around the moon. In 2018, a scientific team confirmed what researchers had theorized for decades. Using data from an orbiting spacecraft and an instrument called the Moon Mineralogy Mapper, they found definitive spectroscopic evidence of water ice on the lunar surface, concentrated in permanently shadowed regions near the poles. This was confirmed science. Specific absorption signatures in the infrared spectrum, exactly matching the molecular fingerprint of water ice, appeared in data from the shaded crater floors. The detection had been anticipated, theorized, modeled, and debated. The confirmation still hit the space science community like a starting gun. Before that confirmation, returning to the moon carried one clear purpose: proving technology and demonstrating human capability in deep space as a stepping stone to Mars. The moon itself was scientifically interesting, but not uniquely resource-rich in any way that would fundamentally change the economics of space exploration. Water ice changed that calculation entirely. Water does three things that transform space exploration economics. First, it keeps people alive. Humans require water continuously. Carrying it from Earth is expensive beyond description, roughly $10,000 per pound to low Earth orbit using current systems, and far more to the lunar surface. A local water source changes the entire supply chain equation. Second, water can be split into hydrogen and oxygen using electricity from solar panels. Liquid hydrogen and liquid oxygen are rocket propellant. The same substance that astronauts would drink could also fuel a return vehicle. A refueling station at the lunar South Pole, drawing on local ice, could reduce the propellant mass that future missions need to carry from Earth by a dramatic fraction. Third, oxygen extracted from water supports life support systems and could supplement or replace consumables currently carried from Earth. The South Pole water ice transformed the Moon from a scientifically interesting destination into something closer to a supply depot and launch pad for deeper solar system exploration. That shift drove Artemis toward the South Pole as its mandatory landing target, even though the poles are technically far more challenging to reach and operate on than the equatorial regions where Apollo landed. The decision to target the South Pole was not unanimous inside NASA. Some mission planners argued that the engineering challenges of South Pole landing were severe enough that attempting them on the first crewed lunar landing in 50 years was unnecessarily risky. Better to go somewhere easier first, prove the system works, then push to the poles. Others argued that the strategic value of the ice was too high to delay accessing it. Every year of delay was a year during which another program, including international competitors, might reach the South Pole first. That second concern, the competitive dimension of lunar exploration, shaped decisions in ways that are rarely discussed openly. And the specific competitor in question had a lunar program moving faster than most American analysts publicly acknowledged at the time Artemis II flew. The decision NASA made in April 2021 to award the Human Landing System contract exclusively to SpaceX changed everything about the Artemis timeline. Before that decision, many people assumed NASA would select 2 or 3 companies to develop competing landers, similar to how commercial crew transportation to the International Space Station was handled. Competition drives development. Redundancy provides backup. Multiple designs reduce the risk that a single technical failure grounds the entire program. NASA selected only SpaceX. The selection was immediately challenged in court by Blue Origin, the company founded by Jeff Bezos, which had submitted a competing proposal. The legal challenge delayed the contract award and the start of funded development by roughly a year. By the time the court upheld NASA's decision and SpaceX could fully begin work on the Lunar Starship variant, months had slipped away. Starship itself was already the most ambitious vehicle in the history of commercial spaceflight. The full system consists of a massive first stage called Super Heavy, over 230 feet tall, and the Starship upper stage, another 160 feet. Together they stand taller than any rocket ever built. The entire system is designed to be fully reusable. The first stage returns to the launch site and is caught by mechanical arms. The upper stage is designed to return to Earth as well. For the Human Landing System, the upper stage of Starship would be modified with landing legs, expanded propellant tanks, and a docking port to connect with Orion in lunar orbit. This modified version, sometimes called the Lunar Starship, would receive a crew from Orion, descend to the surface and return the crew to Orion after the surface mission. The critical dependency was this. Before a human crew could board a lunar starship in orbit above the Moon, the vehicle had to demonstrate it could reliably perform one operation that had never been done operationally before in spaceflight history. It had to transfer propellant from one spacecraft to another in the vacuum of space. The challenge of that single step held up the entire lunar landing. Starship burns liquid methane and liquid oxygen. Both are cryogenic propellants, meaning they must be kept at temperatures far below zero to remain liquid. Liquid oxygen must stay below negative 297 degrees Fahrenheit. Liquid methane must stay below negative 258 degrees Fahrenheit. In the vacuum of space, keeping cryogenic propellant stable inside a tank is an engineering challenge. Tanks must be insulated, vented periodically to manage pressure buildup from small amounts of boil-off, and kept away from direct thermal radiation as much as possible. All of this is complex but manageable for a single vehicle. Now, add a second vehicle, a tanker variant of Starship, launched separately and already carrying propellant, needs to physically connect to the lunar Starship and pump large quantities of cryogenic fluid from one tank system to another. The two vehicles must maintain a stable docking configuration while liquid at extreme temperatures flows through transfer lines under pressure. In microgravity, with no gravity to help direct the fluid naturally toward the receiving tank. In microgravity, liquids form bubbles. They don't sit at the bottom of a container. They float in complex patterns that shift with any vibration or thermal gradient. Pumping cryogenic liquid reliably from one tank to another requires either spinning both vehicles to create artificial gravity, or using pressure differences to drive the flow, or developing specialized equipment to handle the bubbly, unpredictable behavior of cryogenic fluid in space. No spacecraft had ever transferred cryogenic propellant from one vehicle to another in orbit. Fuel transfer in space had been done with storable propellants, chemicals that remain liquid at room temperature and behave predictably in microgravity. Cryogenics added an entirely new category of difficulty. SpaceX planned a series of demonstration tests. The first required Starship to reach orbit, then transfer propellant internally between its own tanks, proving that the pumping and management systems worked before introducing a second vehicle. That internal transfer test was a necessary precursor. It had to succeed, be analyzed, be confirmed, and then a separate tanker to Starship test had to be planned, flown, and validated. Each of those steps carried its own development schedule. Each required Starship to fly successfully in the configuration needed for the test. And Starship's early test flights, while progressively more successful, took time to accumulate the results NASA needed to certify the system for human use. The propellant transfer requirement sat on the critical path for Artemis 3 in the most direct way possible. Without demonstrated certified orbital propellant transfer, the lunar Starship couldn't be fully fueled in lunar orbit. A lunar Starship that wasn't fully fueled couldn't carry a crew to the surface and back. The physics of the lunar landing and ascent required specific propellant quantities that couldn't be reduced without sacrificing the mission entirely. While Artemis 2 was flying its lunar flyby, teams in Texas and Florida were still working through the test campaign required to prove this had been solved. And while engineers focused on propellant physics, an entirely different kind of force was shaping the program's schedule from a direction that had nothing to do with spacecraft. There is an uncomfortable truth about large government space programs that the press releases rarely state directly. The technical problems are real. The funding problems are often worse. Artemis has operated inside a budget environment that changed significantly between its inception and the Artemis 2 flight. The program was announced under one administration, continued into a second, extended through a third, and every transition brought reassessment, recoping, and in some cases, active attempts to redirect funds elsewhere. In the years between the initial Artemis announcement and the Artemis 2 flight, Congress repeatedly appropriated less money for the human landing system than NASA formally requested. The gap between the request and the appropriation, accumulated over multiple budget cycles, represented billions of dollars that the program was officially counted on having and did not receive. Development stretched, schedules slipped, contractors adjusted their plans to match the actual funding rather than the projected funding. The Space Launch System itself became a focal point of congressional politics in a specific way. The rocket's manufacturing is distributed across dozens of congressional districts. Boeing, Northrop Grumman, Aerojet Rocketdyne, and hundreds of smaller subcontractors employ workers in states represented by powerful Senate and House members who sat on the committees controlling NASA's budget. This created a constituency for continuing the program, even when costs escalated beyond original estimates. Some aerospace analysts argued publicly that the Space Launch System should be replaced by commercially developed rockets, specifically SpaceX's Falcon Heavy or Starship, which could perform similar missions at a fraction of the per-launch cost. The political reality was that cancelling the Space Launch System would have eliminated tens of thousands of jobs across politically crucial states. The program continued. The intersection of political preservation and technical development created a program that was sometimes optimized for continued funding rather than earliest possible landing. Decisions about which components to develop in parallel versus sequentially, which contracts to award, and which milestones to prioritize sometimes reflected political as well as technical logic. This is not a scandal. It is how large democratic governments manage expensive long-term programs. But it means the schedule that produced Artemis 2, rather than a crewed landing, was not purely an engineering output. It was the result of technical reality filtered through a political and budgetary process that added years to the timeline. The funding constraints also affected international partners in ways that complicated the program. Several partner agencies committed resources and hardware on the assumption that Artemis would maintain its original schedule. When the schedule slipped, those commitments became misaligned with the actual program timeline, requiring renegotiation and in some cases redesign of partner contributions. All of this, the funding gaps, the political constraints, the shifting schedules, was playing out simultaneously with a development race in another country that some analysts believed was being systematically underestimated by American planners. In October 2020, NASA launched a diplomatic initiative alongside its technical program. The Artemis Accords were a set of principles for responsible behavior in space exploration, covering transparency, interoperability, deconflicting operations, and the release of scientific data. By the time Artemis II flew, over 40 countries had signed. The Accords served multiple purposes. At one level, they were a genuine attempt to establish norms for a new era of lunar activity, as multiple countries and private entities began operating near and on the Moon. At another level, they were a soft power instrument, a way for the United States to establish itself as the organizing center of an international lunar coalition before any other actor could do so. Countries that signed the Accords were implicitly aligning with the American vision of lunar exploration, one that emphasized transparency, avoidance of harmful interference, and a particular approach to resource extraction rights. Countries that did not sign were implicitly outside that coalition. Russia, which had been a critical partner on the International Space Station for decades, did not sign the Artemis Accords. China, which had the second most capable space program on Earth by most measures, also did not sign. Both countries announced their own lunar programs with their own international partners. The emergence of a parallel international coalition organized around China's lunar program changed the strategic framing of Artemis in ways that influenced political decision-making in Washington. The Moon stopped being merely a scientific destination and became, at least in the rhetoric of congressional hearings and agency statements, something closer to contested territory. That framing had consequences for funding. Programs framed as national security imperatives or as competitions that the United States could visibly lose attract different political support than pure scientific endeavors. The language around Artemis increasingly incorporated references to China's lunar timeline and the importance of establishing American presence first. Whether that competitive framing helped or hurt the program is genuinely debated. Proponents argue it sustained political will through budget cycles that might otherwise have cut the program. Critics argue it created pressure to announce optimistic schedules that couldn't be met, damaging NASA's credibility when the schedule slipped. What is confirmed is that the competitive environment changed how Artemis decisions were communicated to the public and influenced some specific choices about mission architecture and prioritization that had tangible effects on the timeline. The most tangible effect was on the decision of whether to delay specific Artemis milestones for technical reasons or to push forward to maintain visible momentum in what some officials described in internal documents that later became public as a race. Races have winners and losers, and the competitor whose program deserved the most serious attention was moving faster than most public commentary acknowledged. China's space program did something remarkable in the decade leading up to the Artemis II flight. It landed on the far side of the Moon. It returned lunar samples to Earth for the first time since the 1970s. It deployed a rover that operated for years beyond its designed lifespan. It built and began operating its own space station in low Earth orbit, the Tiangong station, after being excluded from the International Space Station program by United States law. Each of these accomplishments was real, confirmed, and verified by independent tracking and observation. The pattern they represented was a program moving at high pace, with strong government backing and a long-term strategic vision, centered on the Moon and eventually Mars. China announced plans for a crewed lunar landing with a target timeframe in the early 2030s. That announcement drew various responses from American analysts. Some dismissed the Chinese timeline as aspirational and likely to slip. Others pointed out that China's space program had a track record of meeting or exceeding announced milestones in ways that previous generations of Western analysts had underestimated. The technical capability China had demonstrated included precision landing on challenging terrain, sample return operations, and robotic surface operations in environments with extreme temperature swings. All of those capabilities are directly relevant to a crewed lunar landing program. What China did not yet have in the publicly confirmed domain was a crewed spacecraft rated for lunar distance, a heavy-lift rocket comparable to the Space Launch System's performance, or a demonstrated life support system for long-duration deep space missions. Development on all of these was ongoing, and Chinese space officials described an accelerating timeline. For Artemis program managers, the Chinese timeline created a specific concern. A Chinese crewed lunar landing before an American crewed lunar landing would be a significant symbolic and strategic event. The specific fear expressed in various congressional testimonies was not just being second, but being second at the South Pole, where the water ice resources are located. If a Chinese program reached the South Pole first and established operational infrastructure there, the question of how resource extraction rights work in a location where two national programs both claimed presence would have no clear answer under current international law. The Outer Space Treaty prohibits claiming sovereignty over the Moon, but it does not clearly address simultaneous resource extraction operations by competing parties. This scenario was not imminent at the time of Artemis II, but it was close enough on the timeline horizon to be a genuine planning concern rather than a distant abstraction. The pressure this created showed up most visibly in one specific domain: suits. The Apollo spacesuits were engineering miracles produced under extraordinary pressure. They were also destroyed during use, discarded on the lunar surface, or preserved as museum pieces. By the time NASA decided to return to the Moon, no operational lunar surface suit existed anywhere on Earth. The suits used on the International Space Station are called extravehicular mobility units. They were designed for microgravity operations in orbit. They are essentially personal spacecraft, keeping astronauts alive in the vacuum of space while they work outside the station. They work well for what they were designed to do. They were not designed for walking on a planetary surface. The joint mobility patterns are optimized for floating and reaching, not for stepping, crouching, bending at the knee, or handling tools at ground level. The boots are designed for foot restraints on the station structure. The suit's overall weight and stiffness, manageable in microgravity, becomes a serious problem in 1/6 of Earth's gravity, which the Moon provides. A new lunar surface suit needed to be developed from scratch. NASA initially worked on this internally. The development ran behind schedule and over budget. In 2002, NASA announced it would contract the lunar surface suit development to commercial companies under its Exploration Extravehicular Activity Services program. Axiom Space won the contract to develop suits for the early Artemis surface missions, including Artemis III. The suits Axiom produced, visually distinctive and technically sophisticated, incorporated mobility joints designed for surface work, improved thermal management for the extreme temperature swings at the South Pole, and a suit fit system designed to accommodate a wider range of body sizes than Apollo suits could. The certification process for those suits required extensive testing at every level: materials testing, component testing, integrated system testing, human-in-the-loop testing, with suited subjects performing realistic tasks, and formal safety reviews. Each phase generated data that fed back into design refinements, which then required retesting. The confirmed status at the time Artemis II flew was that Axiom's suits were in advanced development and had not yet completed full certification for lunar surface operations. The certification timeline was one of the factors constraining when Artemis III could fly, sitting alongside the propellant transfer demonstration and the overall human landing system readiness. Suits might seem like the least dramatic bottleneck in a program full of rocket science. A suit is just clothing, at some level of abstraction. At the lunar South Pole, in 1/6 gravity, with temperatures that swing 500 degrees between sunlight and shadow, with abrasive regolith dust that destroyed Apollo suit seals faster than expected. The suit is the difference between a successful surface operation and a crisis that unfolds in minutes. Every hour the astronauts spend outside the lander at the South Pole depends on those suits performing flawlessly. and the data from Artemis 2 would help certify how long those suits needed to keep working. That data, still being analyzed when the capsule splashed down, pointed towards something unexpected about the human body's response to deep space. Something that changed not just the suit requirements, but the fundamental question of who should go to the moon next. There is a specific moment in the Apollo program that space historians return to repeatedly, and that NASA's Artemis planners quietly acknowledged as a missed lesson. It happened in 1962, before a single Apollo spacecraft had flown. A young engineer named John Houbolt spent months arguing against significant institutional resistance that the best way to land on the moon was to split the mission into two vehicles, one orbiting above while the other descended and returned. His colleagues and supervisors pushed back hard. The dominant thinking favored either a direct flight from Earth to the surface or Earth orbit rendezvous where multiple launches assembled everything needed before heading to the moon. Houbolt's approach, lunar orbit rendezvous, won eventually. It became the architecture that made Apollo possible within the decade Kennedy had promised. The key insight was that you only take to the surface what you absolutely need there, leaving the heavier return vehicle safely in orbit. Artemis inherited a version of this logic, but applied it inconsistently. The separation of the crew vehicle from the landing vehicle preserved the core principle. What Artemis did not preserve was the Apollo program's insistence on developing both vehicles in parallel, under unified program management, with integrated testing from early in the development cycle. In Apollo, the command module and the lunar module were developed simultaneously by different contractors, but under a program office that treated them as a single system. Issues discovered in one vehicle immediately informed the design of the other. The interfaces between them were tested early and repeatedly. Artemis separated the human landing system from the rest of the program in a way that created a structural gap in integrated testing. SpaceX developed Starship under a commercial contract with significant autonomy. The interface between Orion and the lunar Starship, the docking mechanism, the crew transfer procedures, the communications protocols, had to be negotiated between two organizations with different engineering cultures, different documentation standards, and different risk tolerances. Engineers who had worked on both the International Space Station program and Artemis pointed out this gap in internal reviews. The concern was that integrated testing, having an actual Orion and an actual lunar Starship practice docking and crew transfer procedures before the mission, was scheduled very late relative to the landing attempt. Late integrated testing means late discovery of interface problems. Late discovery means late fixes. Late fixes means schedule delays. This is precisely what Apollo learned from its early years. The fire that killed the Apollo 1 crew in 1967 accelerated the program's commitment to integrated testing at every level. The lesson was written in loss and never forgotten during the Apollo era. Artemis rediscovered versions of that lesson through delays rather than tragedy, which is the better outcome. But each rediscovery cost time. The one specific decision that would have changed the most was awarding the Human Landing System contract earlier in the program, while Orion and the Space Launch System were still in development, and requiring integrated interface testing as a contract milestone rather than a later addition. That decision was available in 2017. It was not taken. What was taken instead were decisions shaped by budget constraints, political timelines, and an institutional assumption that commercial partners would move faster than traditional aerospace development schedules. Some of those assumptions were partially right. Some were optimistic in ways that became visible only in hindsight. Hindsight, unfortunately, doesn't launch rockets, and there was a dimension of this program that no amount of engineering history could have fully prepared anyone for. Reed Wiseman knew before he launched that Artemis 2 would not land. The crew knew from the day they were assigned. They trained for a flyby. They built their psychological preparation around a mission that reached the moon, circled it closely, and returned home. Knowing something intellectually and experiencing it are different things. The psychological literature on high-stakes human performance in confined, isolated environments is extensive enough to fill a library. Researchers have studied Antarctic expeditions, submarine deployments, simulated Mars missions in isolation facilities, and the long-duration International Space Station missions. Across all of them, a consistent finding emerges. Goal proximity combined with goal denial creates a specific psychological stress that is difficult to simulate in training. For Artemis 2, that dynamic was real in an acute form. The crew flew 240,000 miles. They saw the moon close enough to count craters from the windows. They flew within roughly 5,800 miles of the surface. The landing sites that had been chosen for Artemis 3, the ridgeline near Shackleton crater they had studied in photographs and maps for years, were visible terrain features beneath them. And then they flew home. Publicly, all 4 crew members handled this with the professionalism their careers demanded. Their communications during the mission were focused and mission-oriented. Their post-flight statements described the experience as extraordinary and historically significant. Privately, the debrief data told a more layered story. Flight surgeons and mission psychologists who conducted that the combination of physical confinement, radiation exposure, disrupted sleep patterns, and the specific experience of proximity to an unreached goal produced stress markers in the crew that were higher than expected for a mission with no acute emergencies. This data mattered operationally. Artemis 3 will carry a crew to the surface, meaning the psychological demands will be even greater. The crew will need to transition rapidly from spaceflight mode to surface operations, work efficiently in confined suits in a demanding environment, manage the cognitive load of scientific tasks alongside safety monitoring, and maintain team cohesion throughout. Understanding exactly how Artemis 2's crew responded to their specific stresses gave mission planners and flight surgeons better models for crew selection, training design, and in-flight psychological support protocols for Artemis 3. There was one additional psychological element that the Artemis 2 crew experienced that no amount of simulation or Apollo history had fully captured: the silence of the far side. There was a version of the Artemis planning timeline in which Artemis 2 carried a landing attempt. Engineers and mission architects discussed it seriously, documented it formally, and assessed it against the program's readiness criteria. The scenario required several things to align. Starship's orbital propellant transfer demonstration needed to succeed early enough to allow certification before Artemis 2's launch window. The heat shield investigation from Artemis I needed to close faster than it did. The lunar suits needed to complete their certification on an accelerated timeline. And Gateway, while not strictly required for this scenario, needed enough progress to confirm the mission architecture wouldn't need to change after the fact. None of those things aligned in time. The propellant transfer demonstration was the hardest constraint. SpaceX's Starship test campaign, while impressive in its pace of iteration, had not reached the orbital propellant transfer milestone before the Artemis 2 launch window. The physics were unambiguous. A lunar starship without demonstrated propellant transfer capability could not be certified for human landing operations. No amount of schedule pressure could change that requirement without accepting risks that NASA's safety standards explicitly prohibited. The heat shield investigation added roughly 8 months of additional analysis and redesign time to the overall schedule. That 8 months, occurring at the same time as other critical path items were also delayed, pushed the earliest possible landing opportunity past the Artemis 2 window. What confirmed the flyby as the definitive mission plan was a formal readiness review held approximately 18 months before the Artemis 2 launch. Every program element was assessed against a set of criteria. The human landing system was rated not ready for crewed use. The decision was documented, signed, and the program moved forward with the flyby mission as planned. This process was exactly how the system was supposed to work. The readiness review existed precisely to prevent the kind of schedule pressure from overriding technical judgment that had contributed to past disasters. The review boards held their standards. The mission was defined accordingly. The result was a mission that was ready to fly. That matters more than the alternative of a mission that flew before it was ready. What the flyby produced, beyond the crew experience and the psychological data, was a set of engineering measurements that the landing mission genuinely needed. And the most important of those measurements came from the trajectory itself. Artemis 2 flew what engineers call a free return trajectory. The name describes exactly what it is. The spacecraft follows a path around the moon that, if every propulsion system failed completely after a certain point in the flight, would use the moon's gravity to sling the capsule back toward Earth automatically. Gravity does the work. No engines required for the return. If Orion's service module stopped functioning entirely during the lunar flyby, the crew would still come home. They would need to survive for several days on capsule reserves, manage their systems carefully, and hit the re-entry corridor precisely. But the physics would bring them back. Apollo missions in their early phases used similar trajectories for similar reasons. When Apollo 13's oxygen tank exploded and the service module became unusable, the crew survived in part because the trajectory they were on allowed a lunar gravity assist to redirect them homeward. For Artemis II, the free return path was a deliberate safety choice, appropriate for a first crewed test mission. It accepted some limitations on where the spacecraft could go and what maneuvers it could perform, in exchange for a guaranteed return option if anything went catastrophically wrong. A direct landing approach trajectory is different. To descend to the lunar surface, the vehicle must enter a lower orbit around the Moon, perform precise braking burns, and follow a powered descent profile that commits the crew to the surface. A free return option is no longer available once the spacecraft is committed to that lower orbit. The crew is relying entirely on the lander to get them back to Orion, and Orion to get them back to Earth. Every landing mission, starting with Artemis III, will fly without the free return safety net once descent operations begin. This is accepted because the lander's systems will have been certified to a level that makes the statistical risk acceptable. The engineering judgment is that the probability of total lander failure is low enough that the mission can proceed responsibly. But flying Artemis II on the free return path gave engineers something they needed: real measurements of the trajectory's thermal environment, radiation exposure, navigation accuracy, and communication geometry. The data confirmed that the models used to design the approach trajectories for future missions were accurate or revealed where they needed adjustment. Navigation performance was one area where real data diverged slightly from simulation. The precision of Orion's navigation solution during the lunar approach was better than the conservative estimates used in planning, which meant the approach corridor for landing missions could be defined more tightly than originally modeled. Tighter corridor definition meant more precision in the descent path, which translated into safer approach angles over the challenging South Pole terrain. Every number that came back from Artemis II fed the models for Artemis III, and the numbers that came back from inside the crew's bodies were the ones that surprised researchers most. For approximately 25 minutes during the Artemis II mission, 4 human beings were the most isolated people who had ever lived. As Orion swept behind the Moon on its closest approach, the lunar bulk blocked every radio frequency. Mission control in Houston could not reach the crew. The crew could not reach Earth. The spacecraft's antenna pointed at a wall of rock 2,000 miles thick. Every signal died at that surface. This communication blackout was known, planned for, and thoroughly rehearsed. The crew had procedures for every failure scenario that could arise during the blackout period. They knew exactly when contact would resume and what they needed to accomplish before it did. Knowing all of that made no difference to the experience itself. The far side of the Moon has never been seen from Earth. It faces permanently away, locked in synchronous rotation with our planet since ancient times. Spacecraft had photographed it extensively from orbit. No human eyes had seen it directly since the last Apollo lunar module pilots viewed it during their missions ending in 1972. The terrain of the far side is strikingly different from the near side. The near side, the face visible from Earth, is covered with large dark plains called maria, formed by ancient volcanic eruptions that filled impact basins with basalt flows. The far side is more heavily cratered, more uniformly rough, with fewer of those dark smooth plains. The crust on the far side is thicker, which may explain why ancient volcanic activity didn't break through as easily. The Artemis II crew saw this terrain in the closest human view since Apollo. At their closest approach, the lunar surface was roughly 5,800 miles below. The Moon filled their windows. Individual mountain ranges were visible. The irregular texture of the ancient highland terrain stretched from horizon to horizon, and around them, complete black. No Earth glow, no city lights, no blue atmospheric haze, just the Moon and the stars, unfiltered, at a brightness and clarity that no earthbound observer ever experiences, because Earth's atmosphere absorbs and scatters even the darkest night sky. Several crew members later described this specific view as the moment that permanently changed their relationship with the concept of isolation. The overview effect, the cognitive shift from seeing Earth as home to seeing it as a planet, has been documented by dozens of astronauts in low Earth orbit. At lunar distance, with Earth hidden behind the Moon and every human institution and relationship several 100,000 miles away, the effect is categorically different. Reed Wiseman described it as the first time in his life he had experienced true silence. Sound doesn't travel in space, but in low Earth orbit you always feel connected by radio to the ground below. With that gone, the silence became physical. 25 minutes later, Orion emerged from the Moon's shadow. Houston's voice came through the speaker. Contact restored. 4 humans rejoined the conversation of their species. What they brought back from those 25 minutes, in addition to memory, was data. And one piece of that data, measured by sensors inside the capsule during the blackout, was completely unexpected. The heat shield investigation that followed Artemis 1 is a case study in how the hardest engineering problems are often the ones that don't announce themselves dramatically. When the Orion capsule returned from its uncrewed lunar mission in December 2022, recovery teams pulled it from the Pacific Ocean and shipped it to a facility for post-flight inspection. The inspection team photographed every surface, measured every dimension, and compared what they found against pre-flight baselines and post-flight predictions. The heat shield surface showed ablation patterns. Ablation was expected. The shield was designed to erode under re-entry heating. The question was whether the erosion matched the predictions. It did not. Specific regions of the shield had shed material in chunks rather than eroding smoothly. The chunking pattern appeared in areas where the thermal load was predicted to be high but not extreme. Engineers had expected smooth, gradual surface erosion. Instead, they found discrete loss events, areas where the ablative material had cracked along internal boundaries and separated as pieces rather than burning off layer by layer. The investigation that followed required understanding the physics at multiple scales simultaneously. The avcoat material is a composite honeycomb cells filled with an ablative compound that chars and vaporizes under heating. The bonding between cells and between the avcoat layer and the underlying structure had to be analyzed for failure modes that the original design specifications hadn't fully characterized. Arc jet testing, where samples of heat shield material are exposed to hypersonic hot gas flows that simulate re-entry conditions, produced results that helped identify the mechanism. Under certain combinations of heating rate, pressure, and surface shear, the avcoat material developed internal stress concentrations at cell boundaries that could exceed the bonding strength and cause local separation. The fix involved both material changes, specifically modifying the composition of the bonding compound used during manufacturing, and trajectory changes. The skip re-entry approach adopted for crewed Artemis missions reduced peak heating rates by spreading the thermal load over a longer entry time at lower intensity. Lower peak heating rates meant lower internal stresses in the avcoat material, staying below the threshold where the chunking mechanism activated. Validating the fix required manufacturing new heat shield test samples with the modified bonding compound, exposing them to arc jet conditions, simulating the new re-entry trajectory, measuring the results, comparing against the Artemis I data, and running the numbers through updated computational models. Each step generated new data. Some of that data required additional testing to resolve questions it raised. The full investigation cycle took approximately 14 months from the initial anomaly identification to the final certification of the fix. 14 months of analysis, testing, and review, all running in parallel with every other Artemis II preparation activity, compressing the already tight timeline further. When Artemis II flew its skip re-entry and the heat shield performed within predicted parameters, it confirmed the fix. The crew came home safely through 5,000-degree heat, with the shield doing exactly what the revised models said it would. That validation mattered. And so did the next challenge, which involved what happens to the human body after surviving re-entry, after experiencing 10 days in deep space radiation, after spending a week and a half in the strange physical conditions of microgravity and cosmic bombardment. Going to the moon is difficult. Coming home is, in certain specific ways, more unforgiving. The problem is geometry. When Orion returns from the moon, it approaches Earth traveling at approximately 25,000 miles per hour. To survive, it must enter the atmosphere at a precisely defined angle. Too steep, and the capsule decelerates so violently that the G-forces kill the crew and the heat generated exceeds what the shield can handle. Too shallow, and the capsule skips off the atmosphere like a stone off water and continues into deep space, unable to return. The safe window between those two failure modes is narrow. Engineers describe it as a corridor only a few degrees wide. Every decimal place of navigation accuracy during the multi-day journey home directly determines whether Orion hits that corridor correctly. For Artemis 2, the skip re-entry technique added a layer of complexity to this already precise requirement. In a skip re-entry, the capsule dips into the upper atmosphere, decelerates partially, then rises back above the atmosphere briefly before entering for the final descent. This requires the guidance computer to manage two separate atmospheric interactions, each with its own entry angle requirement, heat load, and parachute deployment timing. The benefit is reduced peak heating and a more controlled landing footprint. The capsule can guide itself to a more precise splashdown location because it has additional maneuvering energy during the second atmospheric entry. The landing zone accuracy improves significantly compared to a direct re-entry. The challenge is that the guidance software managing this maneuver was relatively new, validated primarily in simulation and partially on Artemis 1's uncrewed flight. Artemis 2 was the first time it ran with a human crew depending on it. The navigation performance that impressed engineers during Artemis 2's lunar approach carried through to the re-entry. The guidance system hit the entry corridor within margins, significantly better than its required accuracy specification. The skip maneuver executed cleanly. The parachutes deployed in proper sequence. The capsule hit the water within visual range of the recovery ship. The precision of that re-entry produced measurements that will directly refine the models used for Artemis 3. A landing mission has an additional complication. The crew will have been on the lunar surface, working in pressure suits, exposed to lunar dust and regolith for days before they climb back into the Orion capsule for the journey home. Their physical condition at the start of re-entry will be more fatigued, more stressed, and potentially more dust-contaminated than an Artemis 2 crew flying a pure transit mission. Understanding how an Artemis 2 crew's physiology evolved over the mission gave flight surgeons better predictions for how an Artemis 3 crew will feel on landing day. Those predictions shaped the emergency response protocols staged on the recovery ships. And the physiological data that Artemis 2 returned contained a finding that nobody had fully anticipated from a 10-day flyby mission. It pointed toward a biological risk that will directly shape the medical criteria for selecting who flies to the surface on Artemis 3. Before any human sets foot on the lunar South Pole, NASA planned to send multiple robots, from multiple commercial companies, carrying multiple instrument packages, designed to characterize the landing zone in ways that orbital observation alone cannot achieve. The Commercial Lunar Payload Services Program, a NASA initiative to purchase robotic lunar delivery services from private companies, was designed to create a pipeline of small landers carrying scientific instruments to the moon at a fraction of the cost of traditional government missions. The idea was straightforward. Pay commercial companies to develop the landers. NASA provides the payloads and the funding, and a steady cadence of robotic missions builds up the data needed to operate safely at the South Pole before humans arrive. The program achieved partial success. Intuitive Machines launched a lander called Odysseus in February 2004. It reached the moon and landed near the South Pole region. It was the first American spacecraft to soft land on the moon since the Apollo era, a genuine milestone. However, the vehicle tipped sideways during touchdown, landing at an angle that compromised the positioning of its antennas and solar panels. It operated for several days before losing power, returning data but less than a fully nominal mission would have produced. Astrobotic's Peregrine lander, launched earlier in 2004, suffered a propulsion system failure shortly after launch and never reached the moon. Other missions in the pipeline were in various stages of development and launch preparation as Artemis 2 flew. The data from Odysseus, despite the landing anomaly, confirmed certain terrain characteristics near the South Pole, and provided the first in situ radiation measurements close to the lunar surface. The incomplete nature of the robotic scouting data entering the Artemis 3 planning phase meant that the hazard detection systems on the lunar starship carried more mission-critical importance than originally planned. The precision landing algorithms would need to do more autonomous terrain assessment during descent because the ground truth maps were less complete than the original program assumed. This was not a program failure in the catastrophic sense. It was a realistic outcome of operating on a frontier where new technology meets a genuinely unknown environment. The commercial program accelerated learning, returned useful data, and demonstrated that private companies could reach the moon, even imperfectly. The imperfections created data about failure modes that will make future missions more robust. The robotic program also confirmed something about the South Pole terrain that changed mission planning for Artemis 3 in a specific and important way. The regolith, the loose surface material covering the moon, at the South Pole, had different particle characteristics than the equatorial regolith Apollo had encountered. The South Pole regolith, potentially mixed with ice particles in some locations, behaved differently under simulated landing plume conditions than the models had assumed. Landing a rocket-powered vehicle near a surface of unknown cohesion at an extremely low temperature was a new problem with limited data. The models were updated. The landing protocols were adjusted. The margins were defined more conservatively. And while all of that surface science was developing, a very different category of data was coming in from the Artemis 2 crew directly, data that nobody had expected to be the most operationally significant result of the entire flyby mission. Every human who has spent significant time in space comes back changed. Bone density decreases. Muscle mass shifts. Vision can be altered by pressure changes in the fluid surrounding the brain and spinal cord. The immune system recalibrates. The microbiome in the gut shifts in patterns researchers are still working to understand. Most of this is documented from long-duration stays on the International Space Station, missions lasting 6 months or more in microgravity inside a heavily shielded structure orbiting within Earth's protective magnetic field. Artemis 2 lasted 10 days. It exposed the crew to radiation levels significantly higher than any International Space Station mission. It placed them in the unique gravitational environment of deep space transit. Neither the pure microgravity of orbit, nor the partial gravity of a planetary surface, but the faint gravitational gradient of a trajectory between two bodies. The biological data collected from the Artemis 2 crew during and after the mission produced several expected results. Bone remodeling markers in blood samples confirmed the modest bone density changes consistent with 10 days in reduced gravity. Muscle activity monitors showed expected patterns of reduced lower body use and compensatory upper body activity. The unexpected finding involved the crew's eyes. A condition called spaceflight-associated neuroocular syndrome had been identified in International Space Station astronauts on long missions. It involves changes in the structure of the optic nerve, the retina, and the shape of the eyeball caused by shifting fluid pressures inside the skull during prolonged microgravity. In severe cases, it causes lasting changes to vision. The mechanism is not completely understood, and researchers do not yet have a reliable way to predict which individuals will develop significant changes. What the Artemis 2 data showed was that measurable changes in optic nerve pressure and retinal structure appeared in the crew members more rapidly than researchers expected for a 10-day mission. The rate of change was faster than models based on International Space Station data had predicted for this mission duration. Researchers hypothesized that the higher radiation environment of deep space transit might interact with fluid pressure dynamics in ways not seen in shielded low Earth orbit missions. This finding had direct operational implications. If optic changes progressed during a longer lunar mission at a rate similar to what Artemis 2 suggested, some crew members could experience meaningful vision changes during an Artemis 3 surface mission that affected their ability to perform detailed tasks requiring sharp, close vision. The response was immediate in the mission planning process. Medical criteria for Artemis 3 crew selection were updated to include more rigorous, pre-mission ophthalmological baseline measurements, and specific exclusion criteria for individuals showing certain pre-existing optic nerve characteristics that research suggested might correlate with faster syndrome progression. The suits would need to stay on. The mission would proceed. But who was inside the suits would be decided in part by the data that 4 people brought back from around the moon. The Artemis II biological dataset fed directly into a question that sits at the center of every long-duration space medicine research program. How long can humans safely operate in deep space? And what physiological systems set the hardest limits? For missions to the lunar surface, the duration question had specific parameters. Artemis III's planned surface stay, before the mission was fully locked in, was discussed in ranges from a few days to roughly a week. The thermal constraints at the South Pole, the suit operational limits, the lander's consumables, and the crew's physical endurance all contributed to that range. The bone density data from Artemis II provided a useful reference point for the lower end of physiological impact. 10 days of partial weightlessness produced bone remodeling changes that, while modest, followed measurable patterns. The remodeling markers predicted that a crew doing physically demanding surface work, carrying equipment, collecting samples, working in suits that add mass and resistance to every movement, would experience accelerated bone stress responses compared to astronauts floating passively in the International Space Station. Exercise protocols for lunar surface crews needed to be different from the extensive daily exercise regimens required on the International Space Station. On the station, astronauts spend roughly 2 hours a day exercising specifically to counteract bone and muscle loss. On the lunar surface, the physical demands of surface operations provide some countermeasure effect, but the nature of the loading is different. Station exercise applies controlled, researched loads to specific bone and muscle systems. Surface work applies irregular, task-driven loads that don't follow a research-optimized pattern. Flight surgeons use the Artemis II data to refine the surface work schedules for Artemis III. Rest periods, hydration protocols, and the sequencing of physically demanding tasks versus equipment monitoring tasks were all adjusted based on what the biomarker data suggested about optimal crew performance maintenance over a multi-day surface stay. The vision data pointed toward a harder limit. The rate of optic pressure change seen in some Artemis II crew members, if extrapolated to a 30-day surface mission at the South Pole, projected into a range where vision degradation could affect performance. This drove a specific medical decision. Surface stay durations for early Artemis missions would be kept within a window where the projected optic changes remained within acceptable operational limits based on the Artemis II data. A 30-day surface stay, which some lunar base planning documents had discussed as an eventual goal, moved further into the future. As a result of this data, the biology was setting the schedule as firmly as the engineering was. Researchers were candid that the Artemis II dataset was valuable but limited. 4 people, 1 mission, 1 trajectory, specific solar conditions. More data points were needed. Future missions would expand the biological picture. But for the near-term planning of Artemis III, the data was the best available evidence, and it was treated accordingly. The biology of deep space would continue revealing surprises. The next layer, covering what the Artemis II crew experienced daily inside their capsule for 10 days, introduced questions about human performance in isolated, confined environments that training simulations had prepared for only partially. The Orion capsule was designed to keep 4 humans alive in deep space for up to 21 days. That requirement drove decisions about every system inside the vehicle, from the amount of oxygen stored in the service module to the configuration of the sleeping arrangements. Sleeping in Orion required crew members to anchor themselves against surfaces or use sleeping bags attached to the cabin walls. Without anything to hold the body down, a sleeping astronaut drifts slowly around the cabin, bumping into equipment, disturbing crewmates, and waking repeatedly from the tactile disorientation of floating. The sleep quality data from Artemis II showed that crew members averaged significantly less deep sleep per night than their pre-mission baselines, despite extensive training in simulated microgravity sleep environments. The primary factors were noise from the capsule's environmental control and life support systems, light from indicator panels and windows, and the persistent mild disorientation of floating, which the body's vestibular system never fully accepts as normal, even after days in microgravity. Food on Artemis II was entirely pre-packaged. The caloric requirements for deep space operations were carefully calculated, and the menu was designed to maintain nutritional adequacy over the mission duration. Crew members reported lower appetite than expected in the first few days of flight, a common response to the mild nausea many astronauts experience during adaptation to microgravity. By the mission's midpoint, appetite normalized. The caloric intake data confirmed that crew members consumed enough to maintain the energy balance needed for their workload. Hygiene without running water requires different approaches than anyone on Earth practices daily. Wet wipes, waterless shampoo, no-rinse body wash, and toothbrushing with a swallow-safe toothpaste formulation replaced showers and normal dental hygiene. Waste management in zero gravity involves a system of vacuum-assisted collection that functions reliably, but requires training and adjustment. None of this is comfortable by any residential standard. All of it is manageable by people trained and motivated for the task. The harder daily challenge, documented in crew journals and debrief sessions, was cognitive. 10 days of continuous mission awareness, where every system needed monitoring, every deviation from normal required assessment, and every personal physical symptom needed logging for the medical team, produced a cumulative mental workload that the crew managed professionally and found genuinely taxing. The hardest day, according to crew reports, was day 7. Past the midpoint, with the lunar flyby completed, the mission had entered its return phase. The excitement of the outbound journey and the closest approach had passed. The return journey home stretched ahead with less dramatic content and more routine monitoring. Mission planners had anticipated this psychologically flat phase of long-duration missions and had filled the schedule with science tasks, but the subjective experience of day 7 was the mission's most demanding psychological period. This finding informed the scheduling approach for Artemis 3. Surface missions, with their demanding physical and scientific work on the lunar surface, would have less of the flat return transit psychological problem. But the approach transit and return transit for Artemis 3, during which the crew would be in the capsule for multiple days before and after surface operations, needed carefully designed schedules to maintain engagement and performance. Day 7 data was useful, and the Day 8 data was stranger. At the distance of the Moon, radio signals traveling at the speed of light take roughly 1.25 seconds to make the round trip between the capsule and Earth. That delay is small enough to allow real-time conversation with a slight but noticeable lag. Mission controllers and crew members adapt to it within hours. The communication geometry of the lunar trajectory creates blackout periods beyond the far side passage. As Orion's orbit carried it around the Moon, the lunar bulk periodically interrupted line-of-sight contact with Earth-based relay stations. The primary blackout, the far side transit, was the longest at roughly 25 minutes. Secondary blackouts from certain trajectory phases lasted minutes rather than tens of minutes. For each blackout, NASA had detailed protocols specifying exactly what the crew should do if they experienced any emergency category during the period of no contact. The procedures were designed to allow the crew to manage any foreseeable crisis through at least the duration of the blackout, without needing ground support. The protocols covered engine failure scenarios, medical emergencies, fire inside the capsule, atmospheric pressure loss, and electrical system failures. Each had a specific crew procedure that could be executed without mission control input, with documentation of the crew's actions recorded in the capsule's data systems, so ground controllers could reconstruct events completely once contact resumed. The far side blackout during Artemis 2 passed without any emergency activation. All systems performed normally. Contact resumed on schedule. From the ground's perspective, 25 minutes of silence gave way to a completely nominal status report. From the crew's perspective, the blackout period was one of the mission's most psychologically distinct experiences. They were operating in a region where, if something had gone wrong, the closest help was 240,000 miles away and unreachable for at least 25 minutes. The crew's training in crisis management and their mutual trust developed over years of crew selection and joint preparation was everything they had. The communication architecture for Artemis 3 will be more complex. Lunar surface operations require reliable communication between the suited crew on the surface, the lander, and Earth. The lunar South Pole terrain introduces communication shadowing that low-orbit relay satellites are planned to address. NASA and several partner agencies have been developing lunar relay satellite constellations to provide continuous coverage of South Pole operations. Those relay satellites add another infrastructure dependency to the landing mission. They needed to be in place and operational before surface operations could proceed safely. Their development timeline ran in parallel with everything else. What the Artemis II communications data confirmed was that the signal quality and timing protocols developed for deep space operations performed within specifications. The data compression and error correction systems handled the communication link reliably. That confirmation removed one potential variable from the Artemis III readiness assessment. One variable removed. The list of remaining variables was still substantial. And one item on that list was so unexpected that it emerged not from engineering analysis, but from a single measurement taken inside the capsule on the 8th day of the mission, during a routine medical check. When Artemis II splashed down and the crew was safely aboard the recovery ship, NASA program managers began formally closing out the mission's contribution to the Artemis III readiness picture. The process involved comparing the data returned from Artemis II against the list of open questions that Artemis III's planning required answers to. Some questions closed cleanly. Orion's life support system had performed within specifications for the full mission duration. The thermal control system had maintained safe temperatures throughout the trajectory. The guidance and navigation software had performed at or above required accuracy. The communication systems had worked reliably, except during planned blackouts. The heat shield fix had been validated. Each of those closed items removed a constraint from the Artemis III path. The items that remained open formed the most honest representation of what stood between Artemis II's splashdown and the human being standing on the lunar South Pole. First, Starship's orbital propellant transfer demonstration. This remained the single hardest constraint on the human landing system critical path. The test campaign was ongoing. Progress was measurable and credible. The timeline to completion carried uncertainty that other program elements depended on. Second, the lunar suit certification. Axiom Space's suits had passed multiple intermediate milestones, but had not yet completed the full certification sequence required for human surface operations in the lunar South Pole environment. Remaining tests included thermal performance validation under simulated South Pole conditions and a full-duration human-in-the-loop test of a complete surface excursion scenario. Third, integrated testing between Orion and the lunar starship. The two vehicles needed to practice docking and crew transfer procedures in a relevant environment before the mission. The specific form this testing would take, given that Starship cannot be brought to a NASA ground facility for traditional testing, was still being defined through discussions between SpaceX and NASA engineers. Fourth, the lunar South Pole relay communication satellites. At least initial capability was needed before surface operations could be conducted with the safety margins required for human operations. Fifth, the biological criteria updates flowing from Artemis II's unexpected medical findings. Crew selection for Artemis III required finalizing the updated medical standards before the selection process could close. Each item on this list had an owner, a timeline, and a path to closure. None of them were physically impossible. Each represented genuine specific engineering or operational work remaining. The planning uncertainty around each item, and the way each interacted with the others on the critical path, was the core of why stating a firm landing date for Artemis III remained difficult as of the Artemis II recovery period. The second item on the list, the landing date question itself, had an additional dimension that rarely appeared in technical discussions. While NASA worked through its Artemis checklist, a different category of lunar ambition was developing in parallel at private companies that were not waiting for a government program to set the timeline. SpaceX's long-term stated goal has always been Mars, with the moon as a proving ground and potential refueling stop. Elon Musk has described Starship landing on the moon as a stepping stone in a broader architecture. The commercial incentive to demonstrate this capability independently of the Artemis contract existed alongside the contract work. Blue Origin, after losing the initial human landing system competition and then joining as a subcontractor on later Artemis elements, continued developing its own lunar lander and had its own lunar ambitions that extended beyond the Artemis program. Several smaller companies were in various stages of developing lunar habitat concepts lunar surface mobility systems, and resource extraction technologies oriented toward the water ice at the South Pole. The question of whether any private company would attempt a crewed lunar landing independently of NASA, on its own timeline, using its own certification standards and its own risk tolerance, was actively discussed in the aerospace policy community. No private company had announced a concrete plan for an independent crewed lunar landing. The regulatory environment for such an attempt was genuinely unclear, since current American law gave the Federal Aviation Administration authority over commercial launch, but had ambiguous jurisdiction over operations on the lunar surface. What was clearer was that the technological development being driven by commercial programs, primarily by SpaceX's Starship campaign, was advancing rapidly enough that the gap between NASA's institutional capability and commercial capability was narrowing in specific domains. The propellant transfer technology that Artemis needed, being developed primarily by SpaceX, might be ready before the broader Artemis architecture was ready to use it. The precision landing technology being developed for Starship missions might be validated by commercial lunar cargo missions before Artemis 3 flew. Each of these scenarios would mean that NASA's crewed landing, when it came, would be enabled by technology whose development the agency did not fully control. This dependency on commercial capability was the intended design of the Artemis architecture. The question was whether the dependency created vulnerability if commercial timelines diverged from program needs in either direction, faster or slower. Faster created an opportunity. Slower created the delays that the program had already experienced. The scenario that no planning document had fully addressed was whether a commercial program might simply fly humans to the moon before Artemis 3 on a private mission outside the NASA architecture, and make the question of NASA's landing date less historically significant than it appeared from within the program. That scenario was speculative. The race it implied was real. The most common question about Artemis, from people who care about long-term space exploration, is a reasonable one. Why spend the time, money, and risk on the moon when Mars is the actual destination? The answer is specific and technical, and it matters more than the rhetorical version usually offered in press conferences. Several technologies required for a Mars mission have no realistic way to be developed and validated without going to the moon first. The moon provides a testing environment that Earth-based simulation, no matter how sophisticated, cannot replicate. And the cost of a failure in Martian orbit or on the Martian surface, where a rescue is physically impossible, makes testing those technologies at lunar distance first an operational necessity rather than an optional step. The most direct example is the life support technology for long-duration surface operations. Mars missions will require systems that can sustain crews for months or years on a planetary surface with no resupply from Earth. The life support systems for Artemis surface missions are designed to function for days to weeks, but their core architecture, environmental control, water recovery, atmospheric composition management, is the same architecture that Mars systems will derive from. Operating them in the actual deep space radiation environment at actual lunar surface conditions will reveal failure modes and optimization opportunities that no simulation reveals. The in situ resource utilization technology being developed for the South Pole water ice, the equipment to extract ice, purify it, electrolyze it into hydrogen and oxygen, and store those products, is the same class of technology Mars missions will require to make propellant from Martian atmospheric carbon dioxide and subsurface water. If the technology works at the moon, the lessons learned are directly applicable. If it fails at the moon, the failure happens where rescue is possible, and the cost, though enormous, is survivable for the program. The long-duration spacesuit technology is irreplaceable in this context. The suits that Artemis crews will wear on the South Pole surface will face conditions, dust abrasion, extreme thermal cycling, radiation exposure, operational duration, that will push every system to its limits. Those suits, and the lessons learned from operating them, are the direct predecessors of Mars suits. There is no high-fidelity Mars suit test environment on Earth. The psychological and medical findings from Artemis 2 about deep space radiation effects, optic nerve changes, and cognitive performance in isolated confined environments are also directly Mars relevant. A Mars crew spends roughly 7 months each way in deep space transit, orders of magnitude longer than the Artemis 2 mission. Understanding the biological trajectory that 10 days initiated gives researchers the early data points for extrapolating what 7 months might produce, and for designing countermeasures before the first crew departs. Every Artemis mission is, simultaneously, a data collection mission for Mars. The Moon is the only place in the solar system where that data can be collected with any possibility of crew recovery if something goes wrong. That is why the Moon matters. And that is why everything Artemis 2 returned, from the navigation logs to the blood samples to the sleep quality measurements, carries weight that extends far beyond the next lunar landing. The final data from Artemis 2, the unexpected finding from day 8 that researchers were still analyzing long after splashdown, pointed towards something that extended even further. When the Orion capsule was recovered from the Pacific and its data systems were downloaded, researchers began working through hundreds of gigabytes of sensor readings, biological measurements, navigation logs, and environmental data. Most of it confirmed what models predicted or refined existing estimates with better precision. One measurement did not fit. On day 8 of the mission, during a routine health assessment, one of the crew members showed an unusual pattern in a cardiac biomarker reading. The specific marker, a protein called troponin that the heart muscle releases when under stress, appeared at a low but measurable level in a blood sample. Elevated troponin in any context triggers medical attention because in a clinical setting, it can indicate cardiac muscle damage. The reading was low, below the clinical threshold for a cardiac event diagnosis. The crew member reported no symptoms. All other physiological indicators were normal. Mission control was notified. The crew member was monitored continuously for the remainder of the mission. No additional elevation occurred. The mission proceeded without interruption. Post-flight analysis, combining the troponin finding with the radiation dosimetry data from the same period of the mission, revealed a potential correlation. The day 8 finding coincided with a period of elevated galactic cosmic ray flux, a natural variation in the background radiation environment that the spacecraft instruments had recorded. The timing was suggestive. Researchers were careful about their language. A single data point from one crew member on one mission does not establish causation. Troponin can be elevated by many factors, including physical exertion, dehydration, and minor inflammatory responses. The correlation with cosmic ray flux could be coincidence, but the finding aligned with the hypothesis that had been raised by the cardiovascular health data from Apollo astronauts. The observation that deep space radiation might affect the heart's blood vessels in ways that long-term monitoring had suggested. If cosmic ray flux could produce a measurable cardiac biomarker response in a time frame of days rather than years, the implications for long-duration deep space missions were significant enough to demand investigation. NASA's Human Research Program immediately prioritized additional analysis. New studies examining the relationship between cosmic ray exposure and cardiac biomarker dynamics were initiated using ground-based particle accelerator facilities that could simulate galactic cosmic ray spectra. The question of whether the heart muscle itself, not just the blood vessels, might be directly sensitive to deep space radiation quality became an active research priority. This single data point, a tiny elevation in a protein marker in one person's blood on day 8 of a 10-day flyby mission, opened a line of investigation that could redefine the medical standards for every human mission beyond low Earth orbit planned for the next several decades. It confirmed something that deep space medicine researchers had long believed theoretically. The human body in the deep space radiation environment is not simply experiencing a larger version of what it experiences in low Earth orbit. The radiation quality is different. Galactic cosmic rays, the high-energy particles streaming in from exploded stars across the galaxy, interact with living tissue in ways that the Earth's magnetic field has protected life from for billions of years. Humans evolved inside that protection. Every cell in every human body, across the entire history of the species, developed within the shield of Earth's magnetosphere. Artemis 2 stepped outside it. 4 humans went where no magnetic field reached. They came home changed in ways that researchers are still quantifying, and somewhere in the data they brought back is the knowledge that will decide whether humans can safely go much farther. That question drives everything that comes after Artemis 2. The moon is the first step. The data will tell us whether the next steps are possible and at what cost to the people brave enough to take them.